Chapter 1 talks about structure and bonding. We're going to learn a lot of stuff in this chapter that has to basically serve as a review of general chemistry topics that we learned in previous courses. Organic chemistry, when we hear this term, it has to do with chemistry of organic compounds. Organic compounds, these are compounds that have carbon atom in them. So the structure of an organic compound could consist of several atoms. Most of the time it's a carbon and hydrogen, but you could also have other atoms with that. Now, when you look at a periodic table, any periodic table you come across, it's going to have a bunch of elements, and every single element is going to have a couple numbers around it. A smaller number and a larger number. The smaller number will be the atomic number, which is telling me the number of protons and number of electrons for a neutral element. And the larger number, which is the atomic mass. And the atomic mass, the purpose of it is to tell me how much this element weighs. So what contributes to the mass of the element is actually the number of neutrons. So when you subtract the atomic number from the atomic mass, you get the number of neutrons. So if you have elements that do have the same atomic number but different atomic mass, you know that these are isotopes. Isotopes. The difference between an isotope and another is the number of neutrons. It's very important that we be familiar with the atomic number of that element, so that way we are able to draw the electronic configuration. And it's very important that we draw the electronic configuration correctly, because it tells me how many electrons are in the outer shell versus how many electrons are in the inner shell. Electrons that are in the outer shell usually are the valence electrons. And these electrons are the ones that are going to actually contribute to drawing the Lewis structure of the compound and their chemical reactions as well. So it's very important that we understand correctly how to draw an electron configuration of atoms. So when it comes to those Lewis structures, it's very important that we fulfill a couple of things: the electron count and octet rule. So the electron count, which has to do with the number of valence electrons of those elements within the chemical formula. So for example, if you have CH4, you know that you have 4 valence electrons for carbon, and you have 1 valence for each hydrogen, and you have 4 of them. So that's a total of 8 valence electrons. And those 8 valence electrons have to be on the chemical structure of the chemical formula that you are trying to draw. So the electron count is very important. The second thing is the octet rule. Every single element has to have 8 electrons around it, except hydrogen. Hydrogen has to have only 1. But when it comes to some of these elements that can actually go beyond 8 electrons, these are basically the elements that are actually basically have the expanded octet rule. So the expanded octet rule, like sulfur, phosphorus, xenon, boron, these elements may not fulfill octet rule, and the structure will still be a valid structure. Those chemical structures will have bonds. These bonds, they may be ionic or covalent. And that will depend actually on another factor that's called electronegativity. So we'll come to it in a second. But when it comes to ionic bonding, usually we see them in compounds that have metal bonded to a nonmetal. And when we talk about covalent, we usually see them in compounds that bond nonmetal to another nonmetal. Technically, there are 3 different bonds. One that's ionic, one that is nonpolar covalent, and the third would be the polar covalent bond. And once again, I will revisit this once we talk about electronegativity. This is the bonding patterns that we usually have to fulfill in order for me to come up with a Lewis structure that is valid. So for nitrogen, most of the time you will see it bonded with 3 bonds and having a lone pair. Hydrogen, you will never see it bonded double bond or triple bond. Chlorine, same thing. So these are the common bonding patterns that we usually gonna have to fulfill when it comes to drawing a Lewis structure. and make sure that you always show the non-bonding electrons. So if you are asked to draw a Lewis structure of a certain chemical formula, you don't just have to draw the chemical bonds, you also have to actually show the lone pairs that are actually on those elements within those chemical structures. Electronegativity. It's very important that we understand this concept, as it affects not just chemical bonds type, but also affects the polarity of the molecule. So electronegativity, in terms of definition, it's the ability of the element to attract shared electrons. So if an atom is more electronegative than the other, that means it's going to have the electrons leaning towards it more than the other. And here's an example. You could see here that the carbon and chlorine, the chlorine is more electronegative, pulling those electrons, even though they are shared, pulling them toward the nucleus of the chlorine much closer than they are to the nucleus of the carbon. So this electronegativity trend usually increases from bottom to top, left to right, across the periodic table. So francium would be the least electronegative atom, and fluorine will be the most electronegative atom. So keep that in mind. And based on electronegativity difference between elements, you will basically figure out the type of bond that they have. Meaning, if I have two elements, X and Y, and the bond between them, I want to determine its type. Is it ionic? Is it polar covalent? Or is it non-polar covalent? Well, I need to look at the electronegativity values of those two elements. If the difference is 0.4 or less, that means it's a non-polar covalent. So when you have two elements of the same, right away, you can figure out it's a non-polar covalent bond. Why? Because the difference is 0. If the difference between the two elements, electronegativity values, lies between 0.4 and 1.8, then it's a polar covalent bond. If the difference in their electronegativity comes up to be 1.8 or higher, then it's an ionic bond. So that's the way how we're going to figure out the difference between polar covalent and a non-polar covalent. If I ask a question, what is this going to have, an ionic or covalent? You don't need the electronegativity values, because metal and non-metal will have an ionic bond. Non-metal to another non-metal will have a covalent bond. But what do I need the electronegativity values for? To determine the bond that's covalent, whether it's going to be non-polar versus polar. And this affects dipole moment. The dipole moment, which is basically an arrow that we use to indicate where the electrons are leaning towards. So this dipole moment is going to contribute to what we call molecular dipole moment, that affects basically polarity of the molecule. So when it comes to polarity of the molecules, it's going to depend on dipole moments, which depends on electronegativity. So you could see how important it is to figure out what electronegativity is, because it contributes to not just the bond type, but also contributes to the structure as a whole. Is it going to be polar or non-polar? And for us, in organic chemistry, when we do those experiments, it's very important that we figure out whether the compound is polar or not, because it may affect on me choosing the solvent, me choosing the conditions, temperature versus pressure versus other factors such as catalysts, or it may actually affect me purifying the compound. So if I isolate that compound, it will matter whether it's polar or not to choose the proper purification technique. So it's a very important topic. When we draw the chemical structure, it's very important that we be aware of formal charges. It's very easy to figure out the formal charge of an element by looking at how many electrons around the element belongs to it, and figure out from the periodic table how many valence electrons it's supposed to have. So let's take an example. I know there is a chemical equation here, or a formula that you can follow, or maybe you have done it in general chemistry, but there's a faster way than doing this. Look at the oxygen. Oxygen is supposed to have 6 valence electrons, but how many electrons around the oxygen atom belongs to it? I got an electron right there, bonded to another electron from the hydrogen, same and same with the other two hydrogens. So you have 3 electrons bonded to hydrogens, and you have the 2 electrons that are lone pair. So you have 5 electrons belong to oxygen. It's supposed to have 6, so it lost 1. So the formal charge is +1. If you look at NO plus and triple bond O, if you look at the oxygen here, same thing. 5 electrons belong to oxygen, supposed to have 6, so that's why it's +1. While nitrogen, supposed to have 5 valence electrons based on the periodic table, and it does have 5 electrons around it as well. So that's why the formal charge of nitrogen in the nitrogen oxide is actually on this nitrogen nitroso ion. That's what we call it. Actually, we're going to see this later on in some of the chapters. But this NO plus, it's an ion that where you see the plus is coming from the oxygen, not from the nitrogen. All right. When we draw Lewis structures, we also have to have to take into account resonance forms. So if the chemical structure can be drawn in more than one form, we have to address that. So looking at this structure, we have to actually acknowledge that there is a delocalization of the lone pair on the nitrogen that is possible to basically provide a double bond. Now, these two structures are resonance forms, but one of them will be a major contributor, the other one will be minor contributor, meaning both will exist, but one of them will exist in more than the other. But that's not always the case. You may have a Lewis structure that's going to have 2 resonance forms or 3. They all existed and with the same proportions. So if you take carbonate, CO3 2- as an example, if you look at the structure of carbonate and you draw the 3 resonance forms, you're going to realize that actually the 3 of them have the same exact pattern in terms of bonding and in terms of formal charges. Therefore, they all have the same, they are all equivalent in terms of contribution to the structure. But in this case, there is a difference between the two. What is usually the factors that we have to look at to determine which one is major contributor versus which one is minor? Well, usually there are several factors that we have to consider. When I'm asked a question, choose the major contributor. First, I want to make sure that the central atom is the most needy element, the least electronegative. Central atom to be the least electronegative. Second, the less the separation of charges, the better. If I have 2 structures, one has a +1 and -2, I prefer to have the other if the other structure has only a -1 formal charge. So that's what we mean by the less separation, the better. The third, the negative charge to be on the more electronegative atom. If I have 2 structures, one of them has a negative charge sitting on nitrogen versus oxygen, I will pick the one that's sitting on the oxygen because it's more electronegative. And making sure, obviously, the fourth, which is fulfilling octet rule. I may have the other 3 fulfilled, but if it's not fulfilling octet rule right away, it's not going to be a major contributor. So let's look at an example. So look at an aldehyde functional group on the left versus the resonance form of it. So you could see here that there is a plus charge here and a -1 versus 0 charges. So this will be a major contributor right away. And not just because of the formal charge, also because this carbon right here is not fulfilling octet rule. It doesn't have 8 electrons around it. So that's why it's considered a minor contributor. Let's look at another example. So here, nitrogen, triple bonded carbon, oxygen versus nitrogen, double bonded carbon, double bonded oxygen. You could see the minus charge here is sitting on the nitrogen, while it's supposed to be actually sitting on the oxygen. As you see here, it's actually more preferred to have it on the more electronegative atom. So that's why this structure is a major contributor. Okay? So it's very important that we keep those factors in mind. And let me repeat them once again. In order for me to figure out a structure, whether it's major contributor or not, first, I have to look for the structure to have the least electronegative atom to be the central. Second, the less separation of charges, the better. Lower charges. Third, octet rule to be fulfilled. Fourth, negative charge to be on the more electronegative atom. That's how simple. All right. We're going to learn several ways how to draw a chemical structure or chemical formula, actually. We may draw it as a condensed formula or may draw it as a structural formula. But what I prefer that you try to learn what we call the line angle formula. So this formula, which is sometimes referred to as the zigzag formula, it's very important that we learn how to do it because it's going to make it easier for us when we draw chemical structures to do it fast. Or if we want to draw a chemical equation, or if we want to draw a chemical mechanism for a chemical reaction. So it's very important that we actually be familiar with this line angle formula. So what this formula is about, basically you have carbon going to another carbon, to a third, to a fourth. We don't show the hydrogens. We assume that missing bonds are the hydrogens. So for example, the second carbon, it's connected already to two other carbons. And I know carbon should have 4 bonds. So if it's already connected to 2 other carbons, what are the missing 2? Obviously hydrogens. So I know this is a CH2. I know this is a CH2. I know this is a CH3. The fact that it's connected to only 1 carbon, it's missing 3. These 3 bonds must be hydrogens. Other functional groups, other halogens, other substituents will all has to be basically shown on the chemical structure. And we will revisit this when we start chapter 3. And in that chapter, we're going to learn about alkanes. So we're going to actually start drawing chemical structures and naming them. So we will have to actually practice using this chemical formula when we get to that chapter. Okay. Sigma and pi. And I want to talk about hybridization now. Hybridization. So hybridization is a phenomena that central atoms usually have to actually perform in order for them to build up strong bonds. So if I have 2 elements bonded to each other, such as Cl2. There is no central atom here. Cl attached to another Cl. Or if I have hydrogen, H and not attached to another hydrogen. Usually, the outer shell orbital that is empty is the one that's going to overlap. Meaning, hydrogen, 1s is going to overlap with the 1s of the second hydrogen. If I have Cl2, 2p will have to overlap with 2p of the second Cl. So usually there's no hybridization when I have no central atom. But if there is a central atom, such as beryllium, hydrogen, or if you have BH3, or if you have CH4, the moment you have a central atom in a chemical structure, you're going to have to count what we call electron groups. And this is important that you be familiar with electron groups. So a single bond is 1 electron group. A double bond is 1 electron group. A triple bond is 1 electron group. Lone pair is 1 electron group. So if I have CH4, I have a compound that has a central atom that is carbon, and I have 4 hydrogens around it. I have 4 single bonds around it. That means I have 4 electron groups. And when I have 4 electron groups, it's not only tetrahedral, but it actually has sp3, sp23, sp3 hybridization. So you may learn it in already learned it in Gen Chem, the process of it, which you are not required to know here. However, you need to figure out what type of hybridization every single atom does have. If it's a terminal atom that's not central, the outer shell orbital that's available, that will be the one that's going to be overlapping. If it's a central one, you need to count how many electron groups. If there are 2, like the CO2 molecule, C double bond O, double bond O, what do you have? You have 2 electron groups. That means it's an sp. BF3, I have boron and 3 fluorine attached. That means I have 3 electron groups. How many electron groups? I have 3. That means I have sp2 hybridization on the boron. while the fluorine will basically have the p orbital overlap. So that's the difference between the central versus the terminal. Okay? It's very important that I highlight this now. Also, if I have this structure, which I just seen a minute ago, the aldehyde. Let's say I'm asked a question, what's the hybridization around this carbon and around the oxygen? Carbon has 1, 2, 3 electron groups. That means it's sp2. Oxygen has 2 lone pairs plus the double bond. So you have 3 electron groups. What's the hybridization around the oxygen? Well, it has to be also sp2. So someone might say, okay, didn't you just say the central atoms only? Well, oxygen is also central. Why? Because it has 2 lone pairs and a double bond. So it cannot be considered a terminal. What's considered a terminal here? Hydrogen is a terminal atom. So that's why it will overlap with the s orbital only. So it's very important that we figure out hybridization based on whether it's a central atom or a terminal atom. Going further, if I have 5 electron groups, then it's going to be sp3d. If I have 6 electron groups, then I have sp3d2. So this is important to keep in mind. Whisper theory, it's also important to be aware of. The whisper theory, which tells me basically the bond angle and the shape. So it's very important that we be aware of those rules when it comes to molecular shape and bond angles. So that should be easily visited using the OER, or you could actually visit your reference in the Gen Chem course that you have seen this material with them. All right. Sigma bond versus pi bond. The difference between sigma bond and pi bond. So if I have a sigma bond, that means I'm going to be having no p orbital overlap within it. So sigma bonds usually should have s character within the orbitals that's going to overlap. This is important. While the pi bond is going to always form having p orbital overlap. So that's the first difference between the two. Sigma bond is going to have at least an s character. It could be an s, could be sp2, could be sp3, could be sp2. But in the pi bond, you're going to have a p orbital overlapping one another with another p orbital. And you're going to need 2 p orbitals to form 1 pi bond. You're going to need 4 p orbitals to basically form 2 pi bonds. This is important to keep this in mind. So if I take ethylene as an example, you could see here the C double bond C, the C double bond C. You could see here that the sigma bond that's going to have the sp2 hybridization, while the pi bond, you're going to have 1 p orbital from one carbon and another p orbital from the second carbon. And usually the p orbital electron density is going to be above and below the bond axis. So that justifies the weakness, the reactivity of the pi bond. The fact that the electron density is split above and below the bond axis. What bond axis are we talking about? The sigma bond. The sigma bond electron density is rotating around the bond. So that's why it's stronger. So if I'm going to break a bond within the ethylene, the first bond to go is the pi bond, not the sigma bond. So this is important to keep in mind. So once again, the difference between a sigma bond and a pi bond. The sigma bond is going to have at least an 1s character within those orbitals that's going to overlap. That could be an s, could be an sp2, could be an sp3 orbital. Pi bond is going to have p orbital overlap. You're going to need 2 p orbitals for a single pi bond to be formed. The second difference, the way how the electron density within that bond. Electron density within the sigma bond is rotating around the bond axis. The electron density within the pi bond is split above and below the bond axis. The pi bond is more reactive, weaker compared to the sigma bond. And the last difference is the rotation of the pi bond is rigid, is prohibited. So that's why you see the double bond rotation is 0. When it comes to the sigma bond, it's always rotating around the bond axis. And that will basically tell us now more about the last topic in this chapter, which is isomerism. What is isomerism? If I'm giving 2 chemical formulas And I'm able to draw two different chemical compounds, meaning I have two chemical structures, have the same number of atoms, have the same number of electrons, but different connectivity. The different connectivity will come up with what we call isomerism. But there are two types of isomerism. There is the constitutional one, and there is the stereoisomerism one. The constitutional isomerism, or sometimes we refer to it structural isomerism, is when you have two different connectivity, meaning I have basically pentane, and I have isopentane, and I have neopentane. The difference between these three is just the connectivity, not the number of atoms, not the number of electrons. This has basically 5 carbons in a sequence. This has 4 with a branch coming off the second. This has basically 3 with 2 branches coming off the second. So that's an example of constitutional isomerism. While stereoisomerism has to do with the arrangement. I still have the connectivity the same, but the way how they are arranged in space is different. I could have 2 structures. One has that group in a wedge bond, and the other has a dash bond. Now I'm talking about arrangement in space. I'm not talking about connectivity anymore. Here's another example where I have CH3C double bond C CH3. Same connectivity here. But what is different between these two? The arrangement in space. These two groups cross the double bond are on the same phase. That's why they are cis. These two groups cross the double bond, they are in opposite phases. That's why they are trans. So this is the difference between these two and this structure on the right. This structure on the right has totally different connectivity because the double bond now is in the terminal side of the molecule, while here is in the internal side of the molecule. So these molecules are constitutional isomers, while these two structures, the cis and trans, are stereoisomers. Cis and trans, we're going to learn it in the alkene chapter, and we're going to also learn it in the cyclic alkane chapter. So the cyclic alkanes and double bonds of alkenes usually are rigid bonds. They don't allow for rotation. Therefore, they will generate what we call cis and trans. So those are geometric isomers. Geometric isomers. These are not constitutional isomers. These are geometric isomers.